Hi, good morning, everyone. I'm Allison Sullivan. I'll be the chair of this session. So, this is the demonstration track focusing on verification and validation tools. To give you a quick rundown of what the format is going to be, each tool demonstration will be given 15 minutes. They'll have 5 minutes to give a brief presentation of their tool, and then a combined 10 minutes for a live demo and question and answers. So, as questions pop into mind, feel free to type them into the chat box and we'll go over those. And then for any remaining time at the end of the session, we can cycle back to questions that didn't get answered. First up, we're going to have Kunjin Song presenting his tool for ESBMC Solidity. So, Kunjin, you can take it away and start sharing your screen.
Okay, thank you. Thank you very much, Dr. Sullivan. So I'm going to share my screen. So, okay, let's get started. Hi, my name is Kunjian Song. I'm currently a PhD student at the System and Software Lab at the University of Manchester in Britain. So today I'm going to present to you ESBMC Solidity. So ESBMC Solidity is an open source context-bounded model checker based on the SMT theory, satisfiability module theory. ESBMC Solidity is an extension of the original ESBMC to verify Solidity smart contract for Ethereum blockchain. And smart contracts are computer programs used on the Ethereum blockchain. So I'm going to I'm going to quickly go through the motivations and the architectural overview and also the safety properties we support in ESBMC Solidity. And then the main part of this demo will be the ESBMC Solidity in action. I've got 5 examples to demonstrate, and then I'll quickly talk about the comparison, the experimental comparison, and the future work we are planning. And in the end, I'll show you the link. I'll point you to the link to download and install ESBMC Solidity. So let's get started. The motivations. So there have been 2 noticeable attacks in the past concerning the Solidity smart contract. So I've listed here one in 2016, the DAO attack. The other one is the 2021, happened last year. Both result in loss of multi-million dollars. And the smart contract written in Solidity, once deployed, there's no way to fix the bug in a smart contract. Even the author is not allowed to change it. So the only way to fix it is to destroy the smart contract and redeploy another one. So here comes the research question: how do we apply formal verification to ensure a smart contract is vulnerable free? Then we successfully extended the ESBMC and wrote a new front end, wrote a new Solidity front end for ESBMC to apply the existing verification methodology for Solidity verification. So here's the architectural overview of ESBMC Solidity. So our verification flow uses the Solidity compiler, which is the only external component we use. So the new Solidity front end is essentially a type check engine. It takes the JSON AST as input and performs semantic analysis on each AST node and generates the corresponding symbols. So we have a bunch of internal representations, including the GoTo program, and then the GoTo program will be fit into the symbolic execution engine to generate the SSA form, and then from the SSA form we have the SMT converter module to convert the statement in the SSA form into the logical formula. Here C and not P, where C represents the constraints, and not P represents the negation of the property, of the safety property. So we throw that into the SMT solver. Could be Z3 here. Or ESBMC supports multiple SMT solvers you can use. Then if there is a satisfiability, we the ESBMC will generate a counterexample. If there's no satisfiability, that means there's no property violation happened up to bound K, then the ESBMC will report verification successful. So the properties we supported, so based on the SWC registry, the smart contract weakness classification, our currently is supporting a few properties here, including the integer overflow, integer underflow, authorization through TX origin, static array auto bounds access, dynamic array auto bounds access. So in addition, we also support some code, basic code instrumentations like adding additional constraints using the ESBMC assume function, or adding non-determinism using the non-det function. So let's look at a few examples. So I'm going to stop sharing and then share another screen. I don't know how to switch the screen here. So let's look at a few examples here. First, the first example is pretty straightforward. We have example 1. We copy it here. So in this example, I'm going to show the function underflow vulnerability. So we have a variable here, and then we decremented it twice. Since this variable was a unsigned 8-bit unsigned int, then if you decrement it twice, then it's going to generate a integer overflow problem. So the first step is to use Solidity compiler to generate the JSON-AST. So once we generated the JSON-AST, then we can use ESBMC to verify it. So as you can see here, ESBMC successfully detected this problem and generated a trace of states with some assignment. First x was initialized to 0, and then after the declaration, then after the first assignment x is 1, and then after the first decrement x is 0. Then if you do another decrement, it will become 255, and then the assertion failed. The assert here is a safety property we would like to check. So that's the end of example 1. So the next example. So again, we copy it to here just for convenience. So in example 2, we have the, I'm going to demonstrate the overflow problem. So here we have 3 variables, x, y, z, and another variable sum. So sum is basically x plus y plus z. And as you can see here, the in line 15, it will have the overflow problem, because again we use an 8-bit int. The range, the maximum number that can be represented is 255. So here we again we use the same command, the Solidity to call the Solidity compiler to generate the EST JSON. So once JSON is EST JSON is generated, then we can use ESBMC Solidity to verify the smart contract. And again, ESBMC managed to detect this problem here and pointing you to the exact line number here, which is line 15. After this statement, then after the execution of this statement, sum become 87. Then you have this will fail the safety property here in line 16, as indicated by Solidity, ESBMC Solidity. So that's the end of example 2. Let's look at another example. So example 3. In example 3, I'm going to demonstrate you a loop with a static array out-of-bound access. Here we have we declare a static array that has only 2 elements, and we assign to be 100, and then we have a loop populating the array here. But as you can see here, the boundary is 3. So if I equals 2, then it will fail the it will give us a problem here, the static array auto bound. So let's first generate the JSON EST. And then we can use this ESBM Solidity to verify the program. Okay, yeah, then we have the counterexample generated. So if I equals 2 here, will report A bounds violation, array A upper bound violation. So as you can see here, ESBMC again successfully detected the problem. So that's the end of example 3. Then let's look at another example with respect to dynamic array. Then so here, instead of in this example 4, instead of a static array, we have a dynamic array here. So in this function, the function takes one parameter, the size of the dynamic array, and then declare the dynamic array, and then using a for loop to populate the dynamic array. However, here if n is 0, this function will break. So let's generate the JSON EST first. Poll 4. Okay, and then let's use the ESBMC Solidity to verify it. Yes, now we have the counterexample showing you if the input is 0, then the I is 0. If I is 0, that means the input is 0. Then we have a upper bound violation here. So well, it's not showing the n here. That's a problem we have to fix. Okay, anyway, let's look at the next example, which is example 5. Let's copy it here, example 5. So here I'm going to demonstrate the code instrumentation. We have two hooker functions here, the non-det function and the ESBMC assume function. This function hooks to generate, well, to add additional constraints and non-determinism in the verification process. So here we have 2 variables x and y, and another variable sum. If x, so we assign x to 0 to x, and then we use the non-determinism. We assign non-deterministic value to y, which can be anything between 0 to 255. And here we add another additional constraints here. If we basically limit the range of y between 220 and 255. So within this range, there are only 2 numbers that are also 16. One is 225, the other one is 240. So if we add another constraint to make sure y is cannot equal to 224, then we want to verify the safety property here to make sure sum is not a multiple of 16. Then we can generate the let's generate the EST JSON, and then we can use the ESBM Solidity to verify it. And now ESBMC successfully detected the value that will violate the property sum equals 240. So that's all the demonstrations. Now, okay, we have 1 minute. So I'm going to quickly go through the comparison, experimental comparison. We in our experiment, as you may have read in the paper, ESBMC was the fastest tool out of 5 tools we evaluated. It was able to generate the counterexample for each test case in our benchmark, but the other state-of-the-art verification tools were not able to do that. So in the future, we are going to continually extending this front end to support more data types, and in the end, so hopefully we'll have more verification power for Solidity smart contract. So that's all. Thank you.
Great, thank you for that presentation and demonstration. We have time for a quick question if anybody wants to ask something as an immediate follow-up. Otherwise, we'll take more questions at the end. All right, I'm not seeing any questions in chat or a raised hand, so we'll go ahead and stay on schedule. And up next, we have Alexa Hernandez, and she'll be presenting and demonstrating a tool, Describe. So we'll go ahead and let her take over, and you can start sharing your screen whenever you're ready.
Thank you. So welcome everyone. My name's Alexa. Today I will be presenting Describe, which is a template-based approach. Oh, I think I have the...
You just uncheck Use Presenter View, and it should be fine.
Okay. How do I do that?
It's a setting on the top window bar.
Oh, I think here we
Okay,
go.
yeah, that works.
All right, sorry about that. So I'm here to present Describe, which is a template-based approach to co-generate unit tests and documentation. My colleagues and I have implemented a tool to support Describe for Java, which we describe in a prior publication, the link to which is available on the current slide. In this presentation, I'll mostly do a live demonstration of Describe, but before jumping into it, I'll present a quick motivation behind Describe. Software projects often have numerous specifications, and for each, we typically create a unit test and a documentation fragment. Thus, the specification is redundantly captured in both assets. After producing both assets independently, we must also ensure that they evolve consistently. This is all the more tedious when the specification reoccurs across many functions. When the specification evolves, we must manually update each asset. Without traceability links and tool support, this is an effort-intensive and error-prone process. Describe reduces developer effort and the threat of inconsistencies by allowing developers to specify each specification once using simple templates. After creating templates, developers can invoke these templates using a single Java annotation to generate unit tests and documentation that are consistent and checkable. Describe is most valuable when applied to test and document recurrent specifications. A common example is specifications about exceptions. Here we can see a Describe template to test and document specifications about exceptions. Describe templates comprise two components. The first component is a code skeleton. The code skeleton defines the general structure to test the specification. In Describe, we abstract the test case specific information using placeholders. So for example, the exception type, the focal method, or the state under test. Oops. Placeholders are denoted by surrounding dollar signs. The second component that makes up a Describe template is a documentation fragment. In this template, the documentation fragment references the template's placeholders to document the state under which the exception is thrown. In general, the documentation fragment can capture any kind of specification because it is defined using free-form text. The final step to create a Describe template is to assign it a name. In this case, the template's name is assert throws. To show how to use the assert throws template, we will use the lookup method from Apache Log4j2. The lookup method throws an illegal argument exception when the inputted key is non-existent. In Describe, we invoke templates by adding an annotation with the same name as the target template to the focal method. So to use the assert throws template, we simply add the assert throws annotation to the lookup method and provide a value for each of its parameters. The exception type is illegal argument exception. The state under test is non-existent key. For the parameters, we will pass null as the log event because it's not important for our use case. And we will pass foo as the non-existent key. For the factory method, we will reference an existing Java lookup that we've set up in the corresponding test class. And that's how we invoke Describe templates. So now we're ready to run Describe. There's multiple ways to run Describe. You can use a Java jar file, an Eclipse project, or you can use the Describe Eclipse plugin. So I'll be showing how to use the Eclipse Describe plugin. You simply right-click on the target class in the Eclipse's Project Explorer view and select the Run Describe command. When generation is complete, a dialog appears that lists all of the classes for which assets have been added or modified, as well as any errors that occurred. As we can see, Describe has successfully added the documentation fragment to the lookup method. It has also added a new unit test to the corresponding test class and moved the annotation from the focal method to the generated test. This helps keep production code clutter-free and also helps developers discern which annotation is responsible for which test. Describe also adds an additional parameter to the annotation called UUT, short for unit under test. This helps us keep track of the focal method behind the scenes. Now, if the specification evolves, say, to only throw illegal argument exceptions when the inputted key is null, the outdated documentation will be immediately flagged by this failing test. If we want to update the documentation fragment and the unit test, we simply update the values in the annotation's parameters. So for example, we change the inputted key to null and the state to null key. Now we can simply rerun Describe. As you can see, Describe has successfully updated the placeholder values in both the test and the documentation fragment. So that concludes the live demonstration of Describe. If you've missed any steps or just want a refresher, All of these steps are listed in detail on Describe's README. I'll provide a link on the final slide. All right, swap these one more time. So to summarize, Describe is a template-based approach to co-generate tests and documentation. Describe offers many benefits, including reduced developer effort, increased style consistency, and reduced threat of inconsistencies. Thank you very much for listening, and here are all of the relevant links.
Thank you so much for that presentation. Does anybody in the audience have any questions? We have about 5 minutes before we'll switch to the next presentation. While you might be typing up a question or thinking about raising your hand, I have a quick question. I saw in the demonstration paper the evidence of effectiveness section, and it looks like you did some couple different case studies with end users using Describe. Could you give a little bit of a high-level overview of kind of the conclusions out of that? Did developers find it easy to adopt these assertions, things like that?
Sure. So we did a 4-step investigation of Describe. So one of the steps included a usefulness study of Describe, where we investigated the amount of information inconsistency in a mature software project. And the results were that information inconsistency are prevalent, specifically of the 830-something specifications that we identified, 85% of them were inconsistent. And we found that Describe has a high potential to avoid these information inconsistencies. Specifically, it would have been able to avoid 97% of those inconsistencies. And we also did a comparison study where we compared the quality of the unit tests generated by Describe against existing baselines, as well as the original tests created by the software authors. And the findings were that the unit tests created by Describe are as readable, if not more, than existing baselines.
Great, thank you. So we have a question in chat. So it says, unit test assertions tend to be more scenario/execution specific, while comments should be more generic. How does Describe deal with this mismatch? And any plan to extend Describe to property-based testing or tests?
Yeah, so I think the power of Describe is that it keeps the developer in charge. So it's up to the developers to define templates that are able to handle, to co-generate the unit test and the document fragment. So it's really up to you if you want to create a more flexible template or a more specific one. And for the property-based testing, I'm not too familiar with that, so I don't think I can answer that.
All right, thank you. Any other questions? Or you're welcome to unmute and kind of give your take on property-based testing if you want a little bit of a follow-up. All right. So we'll go ahead and start preparing for the next presentation. Thank you again for your demonstration. So up next, we'll have Kim Hao Nguyen presenting SimInfer. So whenever you're ready, you can go ahead and start sharing your screen.
Yes, I will share my screen now. Okay, can you see my screen?
Yes.
Yes, great. Shall I start now?
Yeah, go ahead.
Yes. So, hi, I'm Kim Hao Nguyen. I'm an undergrad at University of Nebraska-Lincoln. Today, I'm going to present SimInfer, inferring numerical invariance using symbolic states. So program invariants are defined as properties that always hold at certain locations. For example, this cohendiff program does integer division with remainder x divides y with remainder r and quotient q. And so, for example, at L1, we have a loop invariant, which means that it always holds when we enter the loop at every loop iteration, and at the exit of the loop, we have these invariants. And at L2 is the post condition of the program. So we have qi plus r equals x, and r, the remainder, must be between 0 and y minus 1. So suppose that we don't know these invariants beforehand. So SimInfer will help us find those invariants automatically using a combination of static and dynamic analysis. So invariants are really useful for multiple tasks, like for program verification, like in Hoare logic, or for documentation purpose, for testing, debugging, or for code generation and synthesis. And also it can help infer algorithm complexity, as I will show later. So how does SimInfer works? So we start with the source code. So this is the raw cohendiff function in C. SimInfer can also work with Java program or Java bytecode, but I'm going to demo a C program here. Then we will instrument the program with the locations that we want to infer. For example, here we call a pseudo function vtrace L1 to mark a location we want to infer the first invariant, and vtrace L2 to mark the second location. We also have the vasum function to let SimInfer knows the precondition of the function so that it won't generate invalid inputs. Next, SimInfer will do two things. First, it will run the program with some just random inputs, but it must satisfy the precondition, and we collect the concrete states of the program. And secondly, we will use a symbolic execution tool like Cvo for C or SPF for Java. And we run the program through the symbolic execution tool and modify them to output the path condition and variable mapping at the instrumented locations like A1 and A2. So for example, this is a path condition, and if this condition is true, then we have the variable mapping here. And this is a symbolic mapping. So for example, R equals X. So, and the set of all path conditions and variable mappings are the symbolic states of the program. So after this step, we have the concrete states and the symbolic states of the program, and we can use them for the inference step. So at the inference, we use different algorithms for different kinds of invariants. For example, for nonlinear equations, we use an iterative counterexample guided invariant refinement algorithm. And for we use an SMT optimization-based technique. So I'm going to show how the equation invariance inference work. So we start with a set of traces. So this is a concrete traces. Then we run it through the inference algorithm, basically equation solving. Then we get a set of equations. These are the invariant candidates. Then we combine them with the symbolic states we collect earlier, and we use these Z3 to solve for counterexamples. If we found any counterexample, we will add them to the traces set and then start the inference process again. And at the end, we either have no equation left or we have a set of equations without any counterexamples. And finally, at At the post-processing step, we will simplify the equations and remove the redundancy. So for example, for CONDIFF, we found up to 272 invariants, but we were able to simplify and reduce them to only 16 as shown here. And you can see that SimInfer can find the critical invariance for both location L1 to these two equations and L2, this one. And I will show you a live demo how SimInfer works. So I'm going to run SimInfer on the CONDIFF program I showed earlier. CONDIFF. So this is just the code I showed earlier. We have the CONDIFF program, and with vtrade pseudo function to mark the location that we want to infer invariant for. So now let's run if. So here we are running the program through the Civil symbolic execution tool to get the symbolic states, and then we get some symbolic state, and then here we are trying to infer invariance, and then we also generate random inputs for the program to collect concrete traces. Here is the random input, and then finally this is the step that we simplify all the file invariants, and this is the results. So it found both equality invariant for L1 and L2, and these invariants also implies that R must be between 0 and y minus 1. But if in some case we cannot run simple execution, for example, like for another programming language unsupported, we can still use the dynamic inference part of the program. So for example, we have a we can use SimInfer on just the set of concrete traces from a CSV file. For example, this file. So it only has the input variable and the state of each variable. So we can also run it with the concrete traces. So now the program doesn't run the simple execution at all. And you can see it can still infer the correct equality. However, the inequality parts, they may have some spurious invariants, like those, they are correct to our traces, but not correct overall. But because we don't have the simple states to generate counterexample for them, so we don't know if they are real invariant or not. But in general, we found that equalities found by this method are pretty good and precise in most cases. And for the last example, I'm going to show you another application of SimInfer, that is to infer the program complexity. So for example, we have this program. It has 3 nested loops and some complicated control flow. It may be non-obvious to infer the complexity of this program manually. So instead, we use SimInfer to infer the complexity for us by using the invariance. So we have a t counter, the loop counter variable here, and we increase it at every loop iteration. And we, at the post condition, we want to infer the relation between t counter and the input variables m, n, and p. So here so now it's collecting symbolic traces right now. more complicated than the cohendiv, so it takes a while. So it's done now, and it's working to refining the invariant candidates. So this is one candidate, and it is working to, it is finding counterexample for it now. So here we have a invariant involving T counter Mn and P. However, this one looks like quite unintuitive. And however, if we put it into a algebra program to factor it, we have something really interesting. So factor it, and using Sage, factor it. So now we see that this polynomial has three factors: this one, and this one. And because this whole polynomial equals 0, so either one of the three must be 0. So actually, we have found 3 possible bounds for the program. So one of them is this, one of them is this, and the last one is this. And if we do more analysis, we will actually find that this program actually has 3 bounds: t equals 0 when n equals 0, and t equal p plus n plus 1 when n is less than or equal p, and this one when n is larger than p. And actually, this is just solving this equation to get. So yes, that is the end of my demo. Thank you for listening.
Great, thank you so much for that presentation. Does anybody in the audience have any questions for Kim Hao and SimInfer? So while people might be thinking of some questions, I was curious about, so it seems like this tool is pretty easy to use by putting in these V traces, but it does produce a lot of information on the command line screen. Have you tried using this tool with maybe like a small user study? Is it is it too much information on the screen, or are people able to kind of filter through it pretty easily? And do you have any plans to take it from a command line tool to maybe something a little bit more overlaying on top of the code to kind of help make that connection?
Yes, so actually, these output are like the debug output. So I put it in there to help me explain the program, but we can reduce the verbosity of the log. And actually, it would not output much. It just output the end result. And we also have some plan to write some plugin, maybe for VS Code or Eclipse, to integrate these two more into the user workflow. So yeah, that is in our part of our plan.
All right, great. So yeah, we have a question in chat. So Matthew, if you want, you can unmute and ask it, or I can read it, either way.
Yes.
Sure.
So
Yeah,
go ahead.
question. I was thinking about scalability. Like many programming languages that are super useful and interesting, but then I'm always wondering for large programs of thousands of lines, how scalable might it be, both in terms of time. So we saw in the slightly longer example that it takes a bit more time, which is super manageable. But for, let's say, 10,000 lines of code, would it take a day to compute? And also in terms of the output, if I get 100 constraints, I might not want to go through each of them. And maybe to orient my question, is there a way to focus the analysis on only a portion of the program?
Yes. Vo, do you want to answer this question?
Yeah, sure. So I'm one of the co-authors of the paper. And so your question about scalability is, so SimInfer, basically for the symbolic execution part, it depends on the symbolic execution tool. So we use symbolic execution tool to obtain the symbolic states. So if the program that you're trying to feed in SimInfer can be handled by the symbolic execution tool, then then that's about it. After we run the symbolic execution tool, we get the symbolic states, and everything is pretty fast after that. And so for your other questions, sorry, is there a way to focus to a portion of the program? So when we run the symbolic execution tool, we do not get the symbolic states of the whole program. We only get the symbolic state at the location that the user want to. So if the user want at this specific location, then we direct the symbolic execution tool to only get the symbolic states there. So that will help a lot with not having to analyze the whole program. And in general, scalability, symbolic execution is known to have some scalability issue, and that's why most symbolic execution tool will have certain depth. And same thing here, we use symbolic execution tool up to certain depths, and so that helps with scalability.
Okay, thank you very much.
Thanks.
All right, thank you. All right, so we have about 15 minutes left, so we'll go ahead and open it back up to questions from any of the 3 demonstrations. So we started with ESBMC Solidity, and we have Describe and SimInfer as well. So we have another question in chat for SimInfer. So it says, maybe I missed it during your talk, but I was wondering, how do you identify redundant invariants? Do you resort to SMT to check for equivalence and implication between the reported candidate invariants?
So yes, so we do use SMT solver, specifically Z3, to identify and remove redundant candidate invariants. So we check if a set of current a set of some invariants implies some another invariance, then we can just remove that one. And we also have some heuristic to keep some invariance that we think is important.
All right, thank you. So I had a question for our first presentation for Kunjin about the SBMC Solidity. So I was wondering if during any of your time building this tool, since you are working in the smart contract field, have you actually engaged with developers of smart contracts, and did they find it approachable to adopt your tool, or do you have any plan to do that as a follow-up?
Up to now, we don't have any. We haven't verified any real smart contracts from the blockchain, because the software is still in. It's just a prototype. But it's already showing some promising results, and we do have a plan for the future. So we've got some fundings coming from the industry, for us to recruit more PhDs to work on ESBMC Solidity. So we are planning to extend it more to support more complicated language construct and more support more data types for smart contract Solidity. But up to now, our work for Solidity smart contract previous work was like proof of concept. So we selected a few vulnerabilities from the registration list, the SWC registry, and we started from some simple vulnerabilities, and we want to evaluate whether this approach outperforms other state-of-the-art tools. Now it's showing a great results from our evaluation. Yeah.
Great, thank you. So yeah, if you have any questions, feel free to type them in chat, or you can raise your hand and unmute and ask your question as well. So I also had a quick follow-up for Describe. So it was mentioned that kind of the motivation behind it, in relation to someone's earlier question about aligning the scenario and execution specific between the unit test and documentation. And it was mentioned that the motivation for Describe was for recurrent specifications like testing null values, empty strings, and stuff like that. And I was wondering, since you did do some evaluation looking over some existing code bases, how often does this pop up as something that it's helpful to have this type of combined unit test documentation layer for?
Thank you for the question. So we've sort of done two studies along that line. So as I mentioned, we studied a mature software library, which was actually Apache Commons IO. And we found in only 10 classes that there were over 800 specifications about exceptions. So that's pretty prevalent. And in the video for this research demonstration, we showed another use case with a more project-specific recurrent specification in Apache Log4j2. And in that case, the project-specific pattern reoccurred in 100 unit tests. And we were able to create, with one template, we were able to test and document it for 50 of those specifications.
Great, thank you. And then I had another follow-up for SimInfer, and this one is just my curiosity, really. So it was mentioned that this is for numerical invariants and deriving them, and I was just curious what type of kind of bugs would you find by being able to generate these? Like, it looked like a lot of it was valuable for kind of being able to process, like your last demonstration was like a nested for loop on kind of like an individual, almost method level basis. But I was wondering, kind of at a like a high level motivation, kind of what type of bugs in a software program would this be really valuable to help detect?
So I can try to answer that. So so we one way to detect bugs is that if if you as a programmer you write some program and you expect that it should have certain properties. For example, you can say that there's no way at this location you could have negative values, and then you run SimInfer on the program that you wrote, and if it cannot find that, if it cannot say that this at this location is always positive, or if it says that, look, I find something that says that this is negative, then in that case, then you as a developer would say that definitely something is wrong with my code because it gives me something totally unexpected. But that's not that's what finding bugs is not one of the main, is one but not the only main goals of SimInfer, because as you can see that in later stage of development of SimInfer, we found that we could use that for complexity analysis. So finding how long symptotically, how long a program takes to run, linear time, quadratic time, and things like that. So we found several uses, somewhat unexpected uses of SimInfer other than bugs finding.
Great, thank you. So does anyone in the audience have any questions for any of the three?
Sorry.
Oh, yeah. So we have one in chat that says, "Hi, Alexa, great talk. I was wondering what use case you see Describe being used in. For example, based on the scalability of Describe, do you see it generating the test plus documentation for larger projects with more specifications in one go, or as part of a development iteration?"
Yeah, so the way we envision Describe in the software development lifecycle is normally when you test a method, you think of the test case and you write a new test. With Describe, instead of writing a new test, you would select and invoke the appropriate template. And these templates can be created either opportunistically or as part of a larger testing strategy and shared across many projects.
Matthew, were you going to say something before the question in chat?
Yeah, thank you. I just had a follow-up on your question actually about finding bugs and I guess checking specifications. Tanvu, I think you mentioned if you expect some constraint but then you don't find it, does it really tell you something? Can you expect that if SimInfer doesn't produce some constraints that it might be violated, or is there a way to maybe adapt the tool to get these?
What do you mean adapt to get them? Adapt.
So yeah, maybe thinking about a specific example. If I expect that some variable x should never be negative, and I get the constraint x will always be less than 100. Can I assume that it might be any value less than 100, or
so SimInfer will for the property you mentioned is pretty simple. So SimInfer will be able to say that the lower bound of x will be how much, and because of that, you can immediately see that if it said the lower bound of x is -5, then you know that it will be negative.
And so the converse, if I don't see this lower bound, it means that it can reach any value.
The converse, right? So if you do not see that, then the default setting of SimInfer basically said that it has no lower bound, and yeah, so that means that it could reach negative infinity.
Okay, thank you.
Yep.
Great, thank you. All right, so we only have about 4 minutes left. So if you have any burning last questions, feel free to make sure to ask them. In the meantime, in case you're drafting any of those, I want to again thank all of the presenters for your tools and demonstrations. And if you're in the audience and you liked any of these tools and demonstrations, as they all mentioned, they all have publicly available tools. So I encourage you to go check them out and follow up on that. All right, so it doesn't seem like there's any last questions, so we'll go ahead and wrap it up here. Thank you all for joining, engaging in the discussion, and the presenters taking time to prepare all the material to put your tools together and give us a nice demonstration across all 3 tools. It was great to see what they got up to and some interesting use cases of them.
So hi, Alison. Just want to say hi.
Hey.
So not related to SimInfer, but some of our recent works on alloy specification repair.
Oh, yeah.
Yeah. So we it is inspired by your work. Both the for localization as well as a repair.
Yeah, I saw that work. Yeah, I thought it was really interesting, exciting to see another take on how to approach it, and yeah, it was really cool.
Yes. So we never thought about doing specification repair for alloy, but after seeing that someone has already someone already did that and has benchmarks available and things like that, so we decided to try it, and so it works out pretty well.
Yeah, it's an interesting area to repair a specification. It's kind of interesting approaches. Yeah.
Yeah. Are you doing any continued work on alloys analysis?
Yeah, we're still working on it a bit, kind of taking it off in my own direction now as a professor. Definitely focusing on some of the repair and synthesis stuff just to make it more and more approachable to use things like alloy, like not staying just in alloy, but in general, making those type of specification languages more approachable. I think repaired synthesis is a interesting way to approach that.
Okay, yeah. Sorry, I think I saw somewhere that you have a collaboration with the Naval Research Lab. Is that right?
Yeah, yeah.
Is because I used to work at NRL for a while,
Oh, okay.
and so I'm just curious if you work with the ITS group there.
I work with Connie.
Yes, so Connie
Yeah,
had
yeah.
Maya and